Tonight, as you settle into this quiet moment, allow your mind to drift toward one of the most profound questions that has ever stirred human consciousness. Did nothing ever truly exist? This isn't merely an abstract philosophical puzzle to be solved and filed away. Instead, it's an invitation to wonder, to rest in the beautiful uncertainty that connects us to the deepest mysteries of existence itself. Imagine, if you will, a time before time, a moment that preceded all moments. Picture a state so complete in its emptiness that even the concept of emptiness hadn't yet been born. This is the nothing we're contemplating. Not the simple absence of things in a room, not the quiet space between words, but something far more fundamental. We're exploring the possibility of absolute nothingness, a state where space itself hadn't unfurled, where time hadn't begun its eternal march, where even the potential for existence remained unborn. Yet as we begin this gentle exploration, we encounter our first paradox, one that has puzzled thinkers for millennia. The moment we speak of nothing, the moment we contemplate it or give it a name, haven't we already transformed it into something? This isn't just wordplay, it points to something profound about the nature of existence and consciousness. When your mind reaches toward the concept of nothingness, it grasps something real. Something that exists, at least as an idea, as a possibility your awareness can hold. Consider how this question has evolved through human understanding. Ancient philosophers sat beneath star-filled skies, much like the one that might be above you now, and wrestled with these same mysteries. They sensed that the question of nothing touches something essential about reality itself. They understood intuitively that to truly comprehend existence, we must first understand what it means for something to not exist at all. In our modern era, this ancient wondering has taken on new dimensions. Physicists peering into the quantum realm have discovered that what we once thought of as empty space, the vacuum between atoms, the void between stars, is actually alive with activity. They found that nothingness, at its most fundamental level, seems to be unstable, unable to maintain its perfect emptiness. This discovery doesn't diminish the mystery. Instead, it deepens it, adding layers of wonder to our contemplation. But perhaps the most beautiful aspect of this question isn't its answer, for indeed, we may never have a complete answer. Perhaps the beauty lies in the questioning itself, in our capacity as conscious beings to contemplate our own existence and the existence of everything around us. When you pause in a quiet moment like this one, when you allow your mind to reach toward the infinite, you're participating in something remarkable, the universe becoming aware of itself. Think about the extraordinary nature of this moment. Here you are, a collection of atoms forged in the hearts of dying stars, organized into a pattern complex enough to ponder the very foundations of reality. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of it was created in stellar furnaces billions of years ago. You are, quite literally, made of star stuff. And now that star stuff is contemplating whether nothing ever existed. This realization brings a certain comfort, doesn't it? You're not separate from the cosmos wondering about it from the outside. You are the cosmos examining itself from within. When you question whether nothing ever existed, the universe is questioning its own origins through your consciousness. This perspective transforms our inquiry from a cold academic exercise into something warm and deeply personal. As we prepare to explore this question together, let's embrace a spirit of gentle curiosity rather than urgent need for answers. The question of nothing's existence has persisted through thousands of years of human thought, precisely because it touches something essential and mysterious about reality. Philosophers, scientists, mystics, and poets have all offered their perspectives, and each has added something valuable to our understanding, even when they've disagreed with one another. Tonight, we're not seeking to solve this mystery once and for all. Instead, we're choosing to rest in it, to let it carry us into deeper contemplation of existence itself. We're allowing ourselves the luxury of not knowing, of being comfortable with uncertainty while still pursuing understanding. This is perhaps one of the most human of all activities, to wonder about our place in the cosmos without demanding immediate answers. In the sections that follow, we'll explore how ancient minds first grappled with this question, how quantum physics has revolutionized our understanding of emptiness, and how the very structure of reality seems to suggest that perfect nothingness may be impossible. We'll journey from the philosophical heights of abstract thought to the concrete observations of modern science, and then back to the personal meaning these discoveries might hold for each of us. But for now, simply rest in the question itself. Let it settle into your awareness, like snow falling on still water. Did nothing ever exist? As you breathe slowly and naturally, notice how even this simple question opens doorways in your mind, inviting you to explore the deepest mysteries of existence in a spirit of wonder and peace. In the gentle twilight of ancient Greece, nearly 2,500 years ago, a philosopher named Parmenides walked the olive groves and marble pathways of Elea, contemplating a radical idea that would echo through the centuries. As you rest here now, imagine joining him in that timeless moment of wonder, when human consciousness first began to seriously grapple with the nature of nothingness itself. Parmenides, often called the father of metaphysics, arrived at a conclusion so startling in its simplicity that it still reverberates through modern physics and philosophy today. He declared, with quiet certainty, that nothing cannot be. This wasn't merely a clever play on words or an abstract philosophical exercise. For Parmenides, this was a fundamental truth about the nature of reality itself. He reasoned that if we can think about nothing, if we can speak of it or contemplate it, then it must in some sense exist. The very act of negation, he suggested, requires something to negate. Picture the profound implications of this insight. Parmenides was suggesting that existence is so fundamental, so inescapable, that even the concept of non-existence paradoxically confirms the primacy of being. When you try to imagine absolute nothingness, no space, no time, no potential, no possibility, you find that your mind rebels against the task. The harder you try to conceive of true nothingness, the more you find yourself populating it with concepts, with the framework of your own thinking, with the very consciousness that's attempting to grasp it. This ancient insight touches something deeply intuitive about human experience. Have you ever tried to imagine what it was like before you were born? The mind struggles with this task because consciousness cannot easily conceive of its own absence. We can imagine darkness, silence, or emptiness, but these are all something rather than nothing. True nothingness would preclude even the space in which darkness could exist, or the context in which silence could be meaningful. Aristotle, walking in his teacher Plato's garden generations later, expanded on these ideas with his characteristic methodical approach. He argued that nature abhors a vacuum, horror vacui, as it came to be known. For Aristotle, the idea that empty space could exist was not just philosophically problematic, but physically impossible. He observed that when you try to create emptiness, something always rushes in to fill it. Water flows into empty vessels. Air fills spaces where other matter is removed. This wasn't just a casual observation, but a deep principle about the nature of reality. Existence seems to have an inherent tendency to fill any void. These ancient Greek thinkers were grappling with questions that feel remarkably modern. They sensed that the relationship between being and non-being was not straightforward, that existence and nothingness were locked in a dance more complex than simple opposition. Their insights emerged not from sophisticated instruments or mathematical equations, but from pure thought, from the careful application of human reason to the deepest questions about reality. Consider how this ancient wisdom might apply to your own experience. In moments of deep meditation or quiet contemplation, have you ever tried to empty your mind completely, to achieve a state of pure mental nothingness? You may have discovered what these philosophers intuited, that consciousness seems to resist true emptiness. Even in the deepest states of mental quiet, there remains the awareness of the quiet itself, the consciousness that observes its own stillness. The ancient Chinese philosophers approached this mystery from a different angle, one that might resonate with your quest for peaceful understanding. Lao Tzu, the legendary founder of Taoism, spoke of the Tao that cannot be named, the source that existed before heaven and earth. But rather than focusing on the logical impossibility of nothingness, Taoist thought embraced the productive emptiness of the void. They saw emptiness not as the absence of something, but as pregnant potential, the womb from which all existence emerges. This Eastern perspective offers a gentler way of approaching our question. Rather than seeing nothingness as a philosophical problem to be solved, it invites us to experience emptiness as a creative principle. The empty space in a bowl, Lao Tzu noted, is what makes the bowl useful. The hollowness of a flute is what allows it to make music. Perhaps these ancient sages suggested nothingness and existence are not opposites, but partners in the cosmic dance of reality. As you breathe slowly and naturally, consider how these ancient insights might illuminate your own relationship with emptiness and fullness. In the quiet spaces between your thoughts, in the pause between your heartbeats, in the silence between words, there exists something that is both empty and full, absent and present. These ancient philosophers were pointing toward this paradox, this mystery that exists at the heart of experience itself. The remarkable thing about these early philosophical explorations is how they anticipated discoveries that wouldn't be made for thousands of years. Modern quantum physics has revealed that what we call empty space is actually teeming with activity, that the vacuum itself is alive with quantum fluctuations and virtual particles. The ancient intuition that nothingness is unstable, that existence has a tendency to emerge from apparent emptiness, has found unexpected confirmation in the laboratories of contemporary science. But perhaps more importantly, for our present contemplation, these ancient thinkers established a tradition of approaching the deepest mysteries with a combination of rigorous thought and humble wonder. They showed us that the biggest questions about existence, consciousness, and the nature of reality itself are not problems to be solved once and for all, but mysteries to be lived with contemplated, and explored throughout a lifetime. As we prepare to journey forward into more recent discoveries about the nature of nothingness, we carry with us this ancient wisdom, the recognition that existence and non-existence are more intimately connected than they first appear, that consciousness and reality are woven together in ways that exceed our easy understanding, and that the deepest truths often emerge not from aggressive analysis, but from patient, contemplative inquiry into the fundamental nature of what is. The quantum symphony of emptiness. As you settle deeper into this gentle exploration, imagine yourself shrinking down, becoming smaller than an atom, smaller than the particles that make up atoms, until you find yourself in what classical physics once considered the ultimate emptiness, the vacuum of space. Here, in this realm that our ancestors might have called true nothingness, modern science has discovered something extraordinary, a hidden symphony of existence that plays even in the deepest silence of the void. The 20th century brought a revolution in our understanding of emptiness, one so profound that it would have amazed those ancient philosophers we visited in our last contemplation. Quantum mechanics, that strange and beautiful theory that describes the behavior of the smallest constituents of reality, revealed that what we call empty space is actually alive with constant activity. Far from being a passive void waiting to be filled, the quantum vacuum seethes with energy and possibility, like a calm ocean surface that appears still from a distance but reveals countless tiny waves when observed closely. This discovery emerged from one of the most fundamental principles of quantum mechanics, Heisenberg's uncertainty principle. Werner Heisenberg, working in the 1920s, showed that at the quantum level there are limits to how precisely we can know certain pairs of properties simultaneously. The more precisely we try to measure a particle's position, the less precisely we can know its momentum, and vice versa. But perhaps even more relevant to our exploration tonight, there's an uncertainty relationship between energy and time that has profound implications for the nature of emptiness. According to this principle, the energy of any system, even empty space, cannot be precisely zero for any finite period of time. This means that what we call the vacuum, the state of lowest possible energy, still contains residual energy that manifests as quantum fluctuations. Imagine the vacuum as a perfectly still pond that, when you look more closely, reveals tiny ripples appearing and disappearing constantly. These fluctuations represent the temporary creation of particle-antiparticle pairs that pop into existence from the energy of the vacuum itself, exist for the briefest possible moment, and then annihilate each other and disappear back into the void. This process happens everywhere, all the time, even in the space around you right now. As you breathe quietly, as you rest in this moment of contemplation, the empty space between atoms, between molecules, between the stars themselves, is alive with this quantum dance. Virtual particles are constantly appearing and disappearing, borrowing energy from the vacuum for the briefest possible time before paying it back. It's as if existence itself cannot tolerate perfect stillness, as if reality has an inherent restlessness that prevents absolute nothingness from ever truly manifesting. The mathematics of this quantum symphony are elegant in their complexity. Einstein's famous equation E equals mc squared tells us that energy and mass are interchangeable. The quantum vacuum contains enough energy that it can briefly convert some of this energy into pairs of real particles. An electron and its antimatter counterpart, a positron for instance, as long as they annihilate each other quickly enough that the energy books balance. It's like the universe writing itself a very short-term loan, using the borrowed energy to create temporary existence before paying back the debt by returning to the vacuum state. This isn't just theoretical speculation. The effects of these quantum fluctuations have been measured with extraordinary precision. The magnetic moment of the electron, for example, a property that describes how the electron behaves in a magnetic field, has been calculated and measured to more than 10 decimal places. The theoretical predictions only match the experimental results when scientists include the effects of virtual particles in their calculations. The quantum foam of the vacuum isn't just a philosophical concept. It's a measurable, quantifiable aspect of reality that our most precise instruments can detect. But perhaps the most beautiful aspect of this discovery is what it suggests about the nature of existence itself. The quantum vacuum reveals that nothingness is not a static state, but a dynamic process. Emptiness at the deepest level is not the absence of activity, but the ground of all activity. It's not a blank slate waiting to be written upon, but a source of constant creativity, a wellspring from which possibilities continuously emerge and into which they continuously dissolve. Consider what this means for your own relationship with quiet moments like this one. The silence around you, the stillness of the night, the peaceful emptiness you might seek in meditation. All of this apparent emptiness is actually humming with quantum activity. The space between your thoughts, the pause between your heartbeats, the gaps between the words of this gentle exploration, all are filled with the subtle dance of virtual particles, the constant creative activity of the quantum vacuum. This realization can be deeply comforting. It suggests that even in the most profound emptiness, you are never truly alone, never existing in a dead void. The universe around you, even in its most apparently empty regions, is alive with potential, vibrating with the fundamental creativity that seems to be written into the very laws of physics. The quantum vacuum is not nothing in the classical sense. It's better understood as the most fundamental something, the ground state from which all other existence emerges. The implications extend beyond mere physics into the realm of meaning and wonder. If the universe cannot tolerate perfect nothingness even at the smallest scales, if existence has this inherent tendency to emerge from apparent emptiness, what does this suggest about the nature of being itself? Perhaps consciousness, life, complexity, and beauty are not accidents that happened to emerge from a dead, empty universe, but natural expressions of a reality that is creative and alive, even in its most fundamental states. As you rest in this understanding, notice how it might change your perception of emptiness in your own experience. The quiet spaces in your life, the moments of apparent nothingness, meditation, deep sleep, the pause before inspiration strikes. Perhaps these are not empty at all, but pregnant with the same creative potential that fills the quantum vacuum. Perhaps emptiness, properly understood, is not the opposite of existence, but its most fertile ground. This quantum understanding of emptiness prepares us for even more extraordinary possibilities. If the vacuum itself is unstable, if nothingness naturally gives birth to something, then perhaps even the grandest something of all, our entire universe, might have emerged from just such a quantum fluctuation, a brief borrowing of energy from the vacuum that grew into all the stars, galaxies, and conscious beings we observe today. The universe as a cosmic loan. In 1973, as the world grappled with energy crises and social upheaval, a young physicist named Edward Tryon sat in a Columbia University seminar room listening to a colleague discuss the mysteries of cosmology. During a quiet moment in the presentation, Tryon raised his hand and made what seemed like an outrageous suggestion. Maybe the universe is a vacuum fluctuation. The room fell silent. Some colleagues chuckled, assuming he was joking. But Tryon was entirely serious, and his seemingly casual comment would evolve into one of the most profound ideas in modern cosmology. The possibility that our entire universe, with all its stars, galaxies, and conscious beings, might have emerged from the quantum vacuum itself. As you rest here tonight, contemplating the vast cosmos that surrounds you, consider the breathtaking audacity of this idea. Everything you see around you, the walls of your room, the air you breathe, your own body made of ancient starlight, might be the product of the most spectacular quantum fluctuation in history. The universe itself, according to Tryon's hypothesis, might be nothing more than a temporary loan of energy from the vacuum, one that has been running for nearly 14 billion years, but could in principle collapse back into nothingness at any moment. To understand how such an extraordinary claim could be scientifically plausible, we need to explore the remarkable concept of a zero-energy universe. In classical thinking, the universe clearly contains enormous amounts of energy. The light from billions of stars, the heat of stellar cores, the kinetic energy of galaxies rushing apart from each other, the mass energy bound up in every atom. How could all of this possibly add up to zero? The answer lies in one of the most elegant insights in physics, the realization that energy comes in both positive and negative forms, and these might perfectly balance each other out. The positive energy is obvious. It's the energy we can see and feel, the energy that powers stars and heats planets and drives the chemistry of life. But there's also negative energy in the universe, hidden in the gravitational field itself. Einstein's general theory of relativity revealed that gravity is not really a force in the traditional sense, but rather the curvature of space-time itself. Massive objects create depressions in the fabric of space-time, and other objects follow the contours of these depressions, which we perceive as gravitational attraction. But this geometric picture also suggests something profound about energy. Gravitational potential energy is actually negative energy. The more massive an object is, the deeper the gravitational well it creates, and the more negative energy it represents. This insight leads to a remarkable possibility. If you carefully calculate all the positive energy in the universe, the energy in matter, radiation, motion, and all other forms, and then add up all the negative gravitational potential energy, the two sums might exactly cancel each other out. The total energy of the universe might be precisely zero. If this is true, then the universe could have emerged from a quantum fluctuation of the vacuum without violating the conservation of energy, because no net energy would have been created. Picture this cosmic accounting in more familiar terms. Imagine you wanted to dig a hole and build a hill, but you had no dirt to work with. This seems impossible until you realize that you can create both by borrowing dirt from one location to build the hill while simultaneously creating a hole where you remove the dirt. The net amount of dirt remains zero. You've simply redistributed it. Similarly, the universe might have borrowed positive energy from the vacuum to create matter and radiation, while simultaneously creating an equal amount of negative gravitational energy. The cosmic books balance perfectly, even though something magnificent has emerged from apparent nothingness. But Tryon's insight went even deeper. He recognized that if the universe really is a quantum fluctuation, then it shares certain properties with the virtual particles we explored in our previous contemplation. Virtual particles can exist for longer periods if they have less energy, according to Heisenberg's uncertainty principle. A virtual particle with very little energy can persist for a relatively long time before it must annihilate and return its borrowed energy to the vacuum. If the universe truly has zero total energy, then it could persist indefinitely as a quantum fluctuation. It would never be forced by the uncertainty principle to collapse back into nothingness. This perspective transforms our understanding of cosmic history in the most profound way. The Big Bang, that moment of explosive expansion that began our universe's journey, might not have been the creation of something from nothing, but rather the beginning of a spectacular quantum fluctuation that has been unfolding for nearly 14 billion years. Every star that has ever shined, every planet that has ever formed, every living being that has ever drawn breath might be part of an ongoing quantum event, a temporary arrangement of energy borrowed from the vacuum and destined, perhaps, to eventually return. What's truly remarkable about this idea is how it bridges the gap between the quantum world of the very small and the cosmic realm of the very large. The same principles that govern the behavior of virtual particles in the space around you, the uncertainty principle, the instability of the vacuum, the temporary creation of something from apparent nothing, might also govern the existence of the entire universe. The cosmos might be, in essence, a scaled-up version of the quantum phenomena we observe in every cubic centimeter of empty space. This cosmic perspective brings a certain poetic beauty to our existence. If Tryon's hypothesis is correct, then you are not just made of star stuff, as Carl Sagan so memorably put it. You are made of quantum fluctuation stuff, part of a vast and temporary pattern that emerged from the creative instability of nothingness itself. Your thoughts, your dreams, your capacity for wonder and love and contemplation, all of this might be expressions of the universe's quantum nature, ripples in a cosmic fluctuation that has achieved the extraordinary feat of becoming aware of itself. The implications for our original question, did nothing ever exist, are profound. If the universe really is a quantum fluctuation of the vacuum, then even the apparent nothingness from which it emerged wasn't truly nothing. It was the quantum vacuum, that seething sea of virtual particles and possibilities that we explored earlier. True nothingness, a state with no laws of physics, no quantum fields, no potential for fluctuation, might never have existed at all. Yet there's something deeply comforting about this possibility. It suggests that existence is more fundamental than non-existence, that the universe is not a fragile accident that happened to emerge from a dead void, but a natural expression of the creative instability that seems to be built into the very foundations of reality. The quantum vacuum doesn't just permit the existence of virtual particles and fluctuations, it seems to demand them. Nothingness, it appears, is unstable, and existence is what happens when that instability expresses itself on the grandest possible scale. As you rest in this understanding, consider how it might change your relationship with the temporary nature of existence. If everything is ultimately a quantum fluctuation, if even the universe itself is a temporary arrangement that emerged from the vacuum and might someday return to it, then perhaps impermanence is not something to be feared, but something to be marveled at. You are part of the most extraordinary quantum event in cosmic history, a fluctuation that has become complex enough to contemplate its own existence and wonder at its own temporary beauty. The whisper of empty space. In the quiet laboratories of physics, where the most sensitive instruments strain to detect the faintest signals from the quantum realm, scientists have discovered something extraordinary. They can actually hear the whisper of empty space itself. This whisper comes in the form of a gentle but measurable force that emerges from apparent nothingness. A phenomenon so subtle, yet so profound, that it provides direct evidence for everything we've been contemplating about the nature of quantum emptiness. As you rest here in the stillness of this moment, imagine two perfectly smooth metal plates suspended in the most perfect vacuum that human technology can create. These plates are positioned incredibly close together, closer than the width of a human hair, separated by a distance so small that it's measured in fractions of a micrometer. In the classical understanding of reality, nothing should happen in this setup. The space between the plates is as empty as we can make it. The plates themselves are electrically neutral, and there are no obvious forces acting on them. They should simply float there, motionless, indifferent to each other's presence. But in 1948, a Dutch physicist named Hendrik Casimir predicted something remarkable would happen in this seemingly empty space. He realized that the quantum vacuum fluctuations we've been exploring don't behave the same way between the plates as they do in the open space around them. The plates, he calculated, would actually constrain which virtual particles could appear in the narrow gap between them, while the space outside the plates would continue to experience the full spectrum of quantum fluctuations. This tiny difference in the quantum foam would create a measurable force. The plates would be gently pushed together by the pressure of nothingness itself. This prediction seemed almost magical when Casimir first proposed it. How could empty space exert a force? How could nothingness push on something? Yet, the mathematics were clear, and the physical reasoning was sound. The quantum vacuum, as we've learned, is not truly empty, but filled with virtual particles of all possible energies and wavelengths. However, when you place two metal plates very close together, you create a resonant cavity that can only accommodate virtual particles with specific wavelengths, those that fit exactly between the plates in whole number multiples. Picture this like the resonant modes of a guitar string. A guitar string can only vibrate at certain frequencies that fit its length, the fundamental frequency and its harmonics. Similarly, the space between the Casimir plates can only support virtual particles with wavelengths that fit the gap. Outside the plates, in the open vacuum, virtual particles of all wavelengths can exist. This creates an imbalance. There are fewer virtual particles between the plates than in the space around them, resulting in a net pressure that pushes the plates together. The force predicted by Casimir is incredibly small, far weaker than the weight of a feather, more like the pressure you might feel from a soap bubble resting on your hand. For plates separated by 1 micrometer, the pressure amounts to only about 1/100th of a Pascal, roughly 100 billionth of atmospheric pressure. Yet this whisper-soft touch of the quantum vacuum has been measured repeatedly and with increasing precision since the first experiments in the 1950s. These measurements required extraordinary care and patience. The Casimir force is so subtle that it can be overwhelmed by the slightest vibration, the smallest electrical charge, even the thermal motion of atoms in the metal plates themselves. Experimenters had to work in ultra-high vacuum chambers, eliminate every possible source of interference, and use the most sensitive force-measuring instruments available. They had to account for the roughness of the metal surfaces, the exact geometry of the plates, and countless other factors that could mask or mimic the effect they were trying to observe. But the results, when they came, were unambiguous. The plates moved toward each other with exactly the force that Casimir had predicted based on the properties of the quantum vacuum. Empty space was indeed exerting a measurable influence on matter. The virtual particles of the quantum foam, those ghostly fluctuations that appear and disappear in the briefest instants, were creating real, observable effects in the macroscopic world. What makes this discovery so profound is that it provides direct, tangible evidence for the reality of quantum vacuum fluctuations. Until the Casimir effect was measured, virtual particles existed primarily in the mathematical formalism of quantum field theory. They were useful for calculations, essential for making accurate predictions about particle interactions, but their reality remained somewhat abstract. The Casimir effect changed all that by showing that these quantum fluctuations have consequences that extend beyond theory into the realm of measurable physical phenomena. This tiny force whispering between metal plates connects directly to our exploration of whether nothing ever existed. The Casimir effect demonstrates that what we call empty space is not passive or inert, but active and dynamic. The vacuum has structure, energy, and the ability to influence matter. It can push, pull, and exert forces just like any other physical system. In the most literal sense possible, nothingness has been shown to be something. The discovery also reveals the deep interconnectedness between the quantum realm and our everyday experience. The same virtual particles that create the Casimir force between laboratory plates are present in the space around you right now. They're in the gap between your fingers, in the air between the words on this page, in the vast reaches of space between the stars. The quantum vacuum is not some exotic state that exists only in physics laboratories. It's the fundamental background against which all existence plays out. Modern applications of the Casimir effect have moved far beyond confirming theoretical predictions. Engineers designing nanoscale machines must account for Casimir forces, which can be significant at very small scales. The effect influences the behavior of tiny mechanical systems, affects the design of sensitive instruments, and may even play a role in some biological processes at the cellular level. The whisper of empty space, once a purely theoretical curiosity, has become a practical consideration in advanced technology. Perhaps most remarkably, the Casimir effect offers hints about even grander possibilities. Some physicists have speculated about whether the quantum vacuum might be manipulated or engineered, whether its energy might somehow be harvested, or whether understanding its properties might lead to new technologies that we can barely imagine today. The vacuum that once seemed like the absence of everything might actually be the presence of infinite possibility. As you breathe quietly in this moment, surrounded by the apparent emptiness of the air around you, remember that this emptiness is alive with the same quantum activity that pushes Casimir plates together in distant laboratories. The space between atoms, between molecules, between the thoughts in your mind is filled with the constant dance of virtual particles, the endless creativity of the quantum vacuum. You exist not in emptiness, but in the most fundamental fullness, surrounded by and composed of the universe's ceaseless quantum creativity. The Casimir effect teaches us that even our most sensitive instruments can barely detect the activities of the quantum vacuum. And yet those activities are always there, always influencing reality in subtle but measurable ways. It's a reminder that the universe is far stranger and more wonderful than our everyday experience suggests, full of hidden connections and subtle influences that science is only beginning to understand. The inflation of possibility. In the first fraction of a second after the Big Bang, a period so brief that it defies human comprehension, something extraordinary happened that transformed a quantum fluctuation smaller than an atom into the vast cosmos we inhabit today. This period, known as cosmic inflation, represents perhaps the most dramatic example of something emerging from apparent nothingness, and it offers profound insights into our gentle inquiry about whether nothing ever truly existed. As you settle into this moment of quiet contemplation, imagine traveling back in time to the very beginning of everything. Picture the universe when it was younger than a trillionth of a trillionth of a trillionth of a second old, a time so early that the familiar forces of nature hadn't yet separated from each other, when the distinction between matter and energy was meaningless, when space and time themselves were still crystallizing into the forms we know today. In this primordial moment, something happened that would determine the ultimate fate of our cosmic home. The theory of cosmic inflation, developed primarily by physicist Alan Guth in the early 1980s, suggests that during this infinitesimally brief period, space itself underwent a phase of exponential expansion, not the gradual expansion we observe today, where galaxies slowly drift apart from each other over millions of years, but an expansion so rapid and dramatic that a region smaller than a proton could grow to the size of a grapefruit in less time than it takes light to cross an atomic nucleus. This isn't science fiction. It's our best understanding of how the universe we inhabit came to be. What drove this extraordinary expansion? The answer brings us back to the quantum vacuum and its mysterious properties. Inflation theory proposes that the early universe was dominated by a special kind of energy field called the inflaton field. Unlike ordinary matter or radiation, this field had a peculiar property. Its energy density remained constant even as space expanded. Imagine a balloon that, as you inflate it, somehow maintains the same pressure throughout its interior, rather than becoming less dense. This is the strange behavior that the inflaton field exhibited during the inflationary epoch. This constant energy density is reminiscent of the quantum vacuum itself, which also maintains constant energy density regardless of the volume of space being considered. Just as virtual particles continuously emerge from and disappear back into the vacuum, The inflaton field provided a constant source of energy that drove space to expand at an accelerating rate. The universe was, in effect, borrowing energy from this field to create more space, and the field somehow provided an inexhaustible supply of energy to fuel this cosmic growth. The mathematics of inflation reveal something breathtaking about the nature of creation itself. As space expanded, the inflaton field stretched along with it, but rather than becoming diluted, it maintained its energy density by converting its potential energy into the expansion of space itself. This created a feedback loop. The expansion stretched the field. The field provided energy for more expansion, which stretched the field further, providing energy for even more expansion. The universe became a cosmic perpetual motion machine, powered by the peculiar properties of quantum fields. But perhaps the most remarkable aspect of inflation is how it amplifies quantum uncertainty into cosmic structure. During the inflationary period, the quantum fluctuations in the inflaton field, tiny random variations that existed on scales smaller than atoms, were stretched along with space itself. These microscopic quantum uncertainties were inflated to astronomical proportions, becoming the seeds from which galaxies, stars, and planets would eventually form. The quantum foam of the early universe became the cosmic web of matter and energy that surrounds us today. Consider the profound implications of this process. Every galaxy you can see in the night sky, including our own Milky Way, began as a quantum fluctuation during the inflationary epoch. The very atoms in your body, forged in the hearts of stars that formed from matter concentrated by these primordial density variations, can trace their ancestry back to quantum uncertainty in the inflaton field. You are, quite literally, made of crystallized quantum fluctuations that were inflated to cosmic proportions in the first moments after the Big Bang. This cosmic story offers a new perspective on our central question about nothingness. If inflation theory is correct, then our universe didn't emerge from nothing in any simple sense, but rather from a state dominated by quantum fields with properties similar to the vacuum itself. The nothingness that preceded our universe wasn't empty space as we know it, but rather a quantum field configuration that contained the potential for explosive expansion and structure formation. The inflationary universe also suggests that our cosmos might be just one bubble in an eternal sea of inflation. If the inflaton field exists throughout space, then inflation might never truly end everywhere at once. Instead, it could continue in some regions while ending in others, creating a vast multiverse of bubble universes, each with its own physics, its own history, and its own relationship to the quantum vacuum from which it emerged. Our universe would be just one flowering of possibility in an infinite garden of cosmic creation. This eternal inflation scenario paints a picture of existence that is fundamentally creative and inexhaustible. Rather than being a one-time event that happened 13.8 billion years ago, cosmic creation might be an ongoing process with new universes constantly emerging from the quantum vacuum like bubbles forming in champagne. The nothingness we've been contemplating might not be a static void, but an eternally creative source, continuously giving birth to new realities. The observational evidence for inflation comes from precise measurements of the cosmic microwave background, the afterglow of the Big Bang that still fills the universe today. This ancient light carries the imprint of the quantum fluctuations that seeded cosmic structure, and its properties match the predictions of inflation theory with remarkable precision. The universe itself has become a laboratory where we can study the consequences of quantum processes that occurred when reality was younger than a microsecond. As you rest in the quiet of this moment, surrounded by the apparent stability of the world around you, remember that this stability emerged from the most dramatic instability in cosmic history. The solid earth beneath you, the air you breathe, the light that illuminates your experience. All of this traces back to a period when space itself was expanding faster than the speed of light, when quantum uncertainty was being transformed into cosmic structure, when the universe was discovering what it meant to exist. The inflationary paradigm suggests that creation is not a rare or unusual event, but the natural tendency of quantum field systems under certain conditions. Nothingness, in this view, is not a stable state that occasionally gives birth to something, but an inherently unstable condition that inevitably transforms into the rich complexity of cosmic existence. The question is not whether nothing ever existed, but whether nothing could ever truly exist in a universe where quantum fields possess the miraculous property of being able to create space, time, matter, and energy from their own inherent instabilities. This cosmic perspective brings a sense of wonder to the temporary nature of all existence. If our universe emerged from quantum fields during inflation, and if those same fields continue to create new universes elsewhere in the eternal multiverse, then existence itself is revealed as an endless creative process, an inexhaustible flowering of possibility from the fertile void of the quantum vacuum.